So I want to welcome everybody to be here. Thanks for joining for our joint astrophysical colloquium that is organized by our institute, Istituto di Astrofisica e Planetologia Spaziale, the Observatory of Monteporzio and the University of Tor Vergata. And I'm very glad, I'm very proud actually to introduce our speaker for today, that is Professor Leonardo Testi from the University of Bologna, where he's an ordinary professor teaching courses on exoplanets and astrophysical laboratories and techniques. Actually, I'm very proud because Leonardo is a person that in his career lasting more than 20 years, not only mastered the field of star formation and planet formation, but also contribute to shaping the field itself in those years. And my experience was that I met the first time Leonardo in a talk that he held in Volterra for the Lukin School, and I was a master student at that time, and I was impressed by his talk that was talking about the growing dust inside circumplanetary disk. So, to my eyes, I was very impressed and fascinated by the topic. And so, thank you, Leonardo, for that topic that brings me here actually today. I'm saying that he contributed to shaping it because Leonardo in his career, after his formation in Florence, continuing a long-lasting tradition on star formation and planet that was happening there, he moved to Munich. Well, he first moved to Caltech and then to Munich to work with ESO. And he was one of the people that contributed in shaping the scientific work, the scientific plan for the ALMA observatory, the new interferometer. And if you know now that there are those beautiful images of circumstellar disk where we see its structure, and the one with ALMA is thanks to Leonardo work in the early years of 2000 that pushed for this scientific case. After being the project scientist for a long year, he also worked as a head of the support center, contributing to the plan, the scientific plan for the plan for the scientific exploitation, but also the management of this important telescope, shaping also the new plan for the strategy of 2020 for the 2030 years. Moreover, this is just, even if this is a really an important achievement, he also had worked a lot in the field with more than 800 scientific publications with a very high input in the field. Going from the star formation, he was interested in the formation of high mass stars and in clusters, down to the protoplanetary disks, and to the now, I think in the recent years, we moved a lot on the interaction between protoplanetary disk and planet formation. So, sorry for spending so much time for this introduction. I'm leaving the floor to Leonardo for his talk. I just want to add for people that are following from remote, please add your question for the end of the seminar, and then you will have time to interrupt later and ask question for the speaker.
Well, thank you very much, Eugenio, for this introduction, which is a bit a huge load at this point. And thanks for the nice works, of course, and thank you for inviting me to this to the institute to give this colloquium. I have reached, of course, the stage of career in which I mostly present the work done by others, so not things that I'm doing. So I actually enjoy looking at the things with somehow trying to get a different eyes. And what I want to do today, also discussing with Eugenio, we thought it would be nice to try and bridge a bit together what we know of our own solar system from the community of our own solar system, which I am very ignorant, but I am very interested in trying to understand and follow in the field, to what we know actually about planet formation, and trying to understand whether there are some common traits between our own solar system, the formation of our own solar system, and the general processes that we think are important in the formation of planets. Most of what I I will discuss today comes from the work of many people, especially many students and postdocs that have been working not only with me, but with us, I would say, because we, of course, we always worked in groups that have, that included, for example, here, the group here at IAPS, and in particular, many of the results that I will discuss are results that some of you know very well because are results close to EcoGal, the big project that we are working with Sergio and Patrick and Ralph, okay, and the groups in here in Bologna, ISO, and Heidelberg and COA. Okay, having said this, I start on exactly on why this is interesting. Why is interesting for me, for example, to try to join what we know about the solar system and try to understand whether there is something specific or whether there are common traits that we see also in other systems. Because to zero order, of course, you assume that has to be a common trait. So the solar system it has to be, in some sense, the products of planet formation. So why should it be different? So why pose the question? Well, we pose the question because to face value, the solar system is actually still very different from all the planetary systems that we know today. The exoplanetary system science is a field that is 30 years old in the sense of the evolved exoplanets, okay? And we know now of many different architectures, several thousands of planets in thousands of systems, and none of these systems is actually like our own in terms of architecture. So it's a sensible question to ask, is our solar system a bit special? And are there common traits? Is this difference, is the fact that we don't see yet our architecture similar to our own solar system just because we don't have yet the capability of observing it, or is really something peculiar? Okay, and here in this slide there are a few constraints of the solar system that are interesting, and we will get to in a bit more detail later on. On the top left, you have essentially mass distribution in our own solar system. Our own solar system is extremely compact. Well, is compact, let's put it this way. Most of the mass is within the orbit of Neptune, so within 30 AU. And then there is a sharp drop in the mass distribution in our own solar system. We will get to more details on this as well. On the bottom left corner, there is a result from studying meteorites and dating some certain peculiar components of meteorites. We show essentially that our own solar system is 4.5 billion years old, and there are some of the components, in particular some large aggregates of solids, okay, some large aggregates of solids that formed all at the same time. These are the so-called calcium aluminum inclusions that basically are objects of a size of a fraction of a centimeter, roughly speaking, the typical dimension, and which are the white thing here inside this slice of the Allende meteorite, and they have all formed in our own solar system at a very specific time with a very small time dispersion of less than 10 to the 4 years, essentially. So a very precise time in our own solar system, and they formed all together at this time, and they are the oldest objects known in our own solar system. So this is normally taken by people studying our own solar system. This is taken as the zero of the formation, time zero for the formation of our own solar, of the planets, at least in the bodies in our own solar system. And then you have these, inside meteorites, you have these other components, this particular type of meteorites, these other components, which are the chondrules, which are objects that are up to a few millimeters in size, that basically have age that start from the formation of CAIs and then last for a few million years, okay, the formation of these things. So it's basically 4 million years. Okay, so this is, in some sense, gives you a time scale in our own solar system, and this is one of the constraints that you want to compare. Then there are other constraints that regards the chemistry volatiles, which I don't think I will have time to go into, which is in the top left corner. It is interesting in itself, but of course there is no time to go through everything. Going back to the details of the mass distribution of our own solar nebula, this is another plot that has a long history, essentially, and has been revisited many times, and is basically showing the mass distribution of in our own solar system, okay, as a function of distance from the star in terms of gas surface density. So considering as if you take the planets and you average their mass in their orbit, essentially, what you would get as a surface density. And then you get the very famous minimum mass solar nebula, which is in the formulation, for example, of Hayashi 81, which is a power law, essentially, that goes down very high surface, relatively high surface density in the inner solar system, and down to the orbit of Neptune, and then you have a sharp cutoff. And this gives essentially the minimum amount of mass that you need to have in order to form your planets. If you take this in modern terms, it is expected that the minimum mass in the solar system should be around 80 Earth masses in terms of solids, roughly speaking, and then a factor of 100 more in gas, very roughly speaking. The interesting thing that this plot shows, which is relevant for some of the discussions that we will do, is two things. Well, the first thing, I already said, the cutoff at the outer edge, but the other, which is at 30 AU, this is important. And the other thing is the deficit of mass around Mars and asteroids, which in the solar system community, or at least part of it, as far as I understand it, has been interpreted as an effect of dynamical interaction, an effect of Jupiter on the formation of the inner planets. Okay, so essentially an effect of the formation of Jupiter on the global evolution of the disk. Okay. All right, this is the basic things from which we will start in our own solar system, and then I now switch to the formation of stars and the formation of planets, what we know in the galaxy, or what we would like to know. So this is the realistic, in quote, picture of our own galaxy, as seen from the top. Of course, people here know it very well, since they have contributed here to actually shape this view of our own galaxy with the Huygens and many other projects. And then you have, my summary of star and planet, with our summary, because we wrote this together with Sergio and Ralph and Patrick, of the formation of stars and planetary system in the Milky Way. Out of the diffuse interstellar medium, you form dense clouds, dense molecular clouds. So the clouds are dense enough that they can start to cool down because radiation does not penetrate inside anymore. So it cools down, they fragment under the effect of gravity, and they are supported against this by a variety of different phenomena that go from magnetic fields, thermal pressure, to turbulence, and potentially feedback from stars, as we will see in a moment. They fragment in smaller clumps, and then these clumps fragment in cores, even little structure, this is a lot of the science that is actually doing here. And once you are at the core, then you fragment you collapse into an individual stellar system, and at the center of this stellar system, you form the protostar, obviously, and also the disk around it as a way to store a regular momentum during the collapse. And inside this disk, you may eventually form planets. So starting from this and trying to think in terms of our own solar system, one of the obvious questions that there is, we are there, as indicated by the arrow. Why we are not in other direction? That's this process depends on other location. What is the physics that really drives this process, and how we can constrain it through the galaxy and compare with our own solar system? These are the questions that we set out to answer with Sergio, Ralph, and Patrick many years, or at least this is my way of the questions that we wanted to answer. I mean, they had slightly different questions, but the bottom line is that we wanted to put together all of these, trying to understand not only the things that I described verbally so far, but also the effect of forming small-scale objects on the rest of the galaxy. And this is the great journey of EcoGal that we are still working on. The three main questions regards the origins of planets, the origins of stars, and the galaxy as a whole ecosystem forming stars. Okay, so today obviously I focus only on the first part and whether what we know of planet formation can be compared with our own solar system of note. Okay. All right. Having said that, the other interesting thing that we know about our own solar system, some of these things are a little bit debated. We can discuss later on the debate about this, but basically one of the points is that nowadays the sun is an isolated star wandering through the galaxy, but this most likely was not the case at the formation time. So at the formation time, the sun formed as part of a group, let's call it like this, which could have been a very dense cluster or a bit smaller, looser aggregates. Here there is some debate about this, but it's connected essentially to these 3 points. I mean, this belief that we formed not in the isolation as we are now, but in a cluster. Essentially, this is connected to statistical arguments. The majority of stars form clusters, so most likely also the sun formed in a cluster. The isotopic abundance, and especially the radioactive isotopes that are so handy for a number of reasons, including some of the dating that I discussed on the meteorites formed had to be injected in the solar system and could be injected by other companions, let's say, in the cluster environment. And the small disk radius, as we will see in a moment, in a little while, the size of the solar system is small compared to the disks that we observe in general in isolated star forming region. And so one option is that indeed there was an event that basically truncated this disk, and I will discuss a couple of these potential effects to truncate the disk as we observe. So getting working. Okay. All right. So here is now a focus on planet formation, starting from a core. Okay, starting from the core. As I said before, cores are substructure within clumps that are substructure within molecular clouds, which are substructures in the galaxy. Okay. From the core, which is typically an object that can undergo collapse. So if you think very classically, is a Jeans mass object, very classically. Now we think it's a bit more complicated, but roughly speaking, you can take this as an order of magnitude of the mass and size of the object. This will collapse under gravity as it cools down. The density reaches the collapse conditions, and it starts forming essentially a star at the center by gravitational collapse. Typically, not all material will fall onto the central star, but the core in itself will have some sort of an average angular momentum that will basically create essentially the fact that not all material can fall on the star, and so you will form what is called an accretion disk at the beginning. And this accretion disk, which typically accounts for 10% of the mass of the star plus disk, okay, throughout the life, at least repeat planet formation. At some point, this object, the first stage, mediates accretion onto the star. Then later on has to be the place where planets form, and then the disk is dissipated, the planetary system appears, and then secondary thing can happen, like the disks or other things. But the main, classically, the main view of planet formation is through these phases. So collapse, formation of an accretion disk, which lasts typically 10 to the 5 years. And then after this initial 10 to the 5 years, collapse fades. There is no envelope anymore. You are left with a star and disk. And this inside this disk, which is now called protoplanetary disk, you have planet formation. This is the typical view. If you look at the statistics of lifetime of these disks, the so-called class 2 disks, they are basically, you have on the top left, again, a classical result at this point. which is the fraction of stars which still have a disk as a function of age of the population. As the populations evolve, the number of stars with disks decline because the disks are dissipated either through planet formation or through dissipation mechanisms. And the e-folding time, this yellow curve is an e-folding fit to that data points, is of the order of 2-3 million years. If you see the graph, basically, at formation, essentially, data are consistent with every star having a disk. And within 10 million years, basically only a tiny minority of the disks are still existing. If you couple this with the statistics of exoplanets, which tell you that at least 80% of the stars should have a planetary system, this means that planet formation has to occur before the disk is dissipated. Okay, so a few million years. That's the typical thing, which is consistent, if we go back to our own solar system, is consistent with the timeline that I was showing for the growth of the solids in our own solar system. Okay, although, I mean, the solids that I was discussing are a few millimeters in size, while a planet is thousands of kilometers in size. So there is a little bit of space in between the two, okay? So we will discuss this point, okay? This is a classical view. And the modern view is a bit more dynamic, but before we go there, I go again on the comparison with the solar system. So with the solar system, what do you expect? You expect, as I said, that CIAs form very early on a narrow time, okay? This time frame is consistent with the main accretion phase in the protostar. So when really you have the gravitational collapse, okay? 10 to the 4 years, roughly speaking, okay? So that's the timescale for CIA formation. At that time, in the first, let's say, million year, you also have to form two other things in our own solar system. So in our own solar system, you have to form in the first 1-2 million years also the planetesimals that will differentiate, and they will give origin to the iron and the stony meteorites. Okay? These are differentiated bodies. They are melted through the aluminum-26 decay, so they need to be formed before the aluminum-26 disappears. So that's why you have 1 or 2 million years. And you have to form the gas giants. Jupiter is thought to be formed within the first 2 million years of our history, let's say. Okay. At the same time, you have all these chondrules formation, so these tiny little silicate things that have an age that span from the age of KAs to 3 million years, which is very similar to the time scale of Jupiter formation. Okay, so there is a connection between these two time scales. Then the formation of terrestrial planets has thought to take to basically require a bit more time. So several million years, from 10 to 50 million years, inside the region of this terrestrial planet formation. And this time scale also needs to align with the formation of what are the non-differentiated meteorites that arrive on Earth. So the components of these meteorites were already present, so CIAs and chondrules, but they are assembled into the body after the aluminum-26 has been dissipated. Okay, so that's the general view that we have in our own solar system. And these steps are very important in the solar system because it's thought that at least one of the views of our solar system is that the early formation of Jupiter actually influenced dynamically very much the solar system, creating the mass deficit at the asteroid and Mars region, and creating the conditions for producing chondrules, for example, in collisions between asteroids, because the chondrules require very high energetic formation times the formation conditions that you don't expect throughout the disk. You need to melt the silicates. And the only way to melt the silicates is either to go very close to the star, but then you have to remix with the rest of the disk, or have very energetic collisions between small bodies. Okay, so this is just to give the thing. Okay, where are we, and what do we want to check in the planet-forming disks, let's say? Okay, so first, the sun formed in a clustered environment. So we need to understand formation of disks and evolution of disks in clusters to make sure that their evolution matches with the solar system. The early solar system nebula, let's call it this way, the disk that formed the solar system needed to be small because the solar system is small, as I said, 30 AU, but relatively massive. Okay, there was a lot of mass, so between 80 and 100 Earth masses of solids are minimum needed to form the planets, especially now that we have the measurements of the cores of Jupiter and of Saturn that are in the 30, 15 to 30 Earth masses. Then you need to have a lot of solids to form this. You need to have a quick formation of Jupiter close to its position. Then it has migrated a little bit in and out, depending on the model that you believe, but more or less the formation close to the snow line. You have to have a strong mixing of planetesimals due to the dynamical interaction between the planets and the disk. And okay, this is the part that I said I would not discuss in detail, which is the part on volatile. Okay, so what do we know of extrasolar disks? So disks in star-forming regions, so young disks younger than these 3 million years. That is the time scale for disk dissipation in terms of masses, sizes, growth of solids, and so on. Okay, what we know came in the last decade, more or less, from decade and a half now. I'm getting older by the day. Every day I'm 1 day older. Two main advances in observational techniques. One based essentially on surveys at low spectral or spatial resolution. So the advent of very large telescope instruments that were very effective in measuring the properties of young stars and star-disk interaction, which is critical in understanding the evolution of disks, as we will see in a moment. Then the surveys of disk populations from ALMA, which has allowed to basically have samples of several hundreds of disks that can then be studied statistically in order to understand the global properties of the populations. And also the other key breakthrough has been basically the advent of high contrast imaging to study the presence or lack thereof of planets within disks, as we will see at some point, and the imaging of disks at high angular resolution with ALMA, which has revealed the inner structure of the disk. Okay, so I'll try to get some of these results, starting from this very simple one. How many disks at 2 million years have enough mass to form the solar system? Simple question. Simple answer, less than 5%. So this is very disappointing to some extent. If you look at this plot, which is cumulative distribution of disk masses in Earth masses for young star-forming regions, so these are all 1 to 5 million years old. Basically, the solar system sits here. Okay, so only a tiny fraction of this have enough mass if our masses are correct. So this is somewhat disappointing, you may think. The second way of looking at the same thing is to look at the average mass of disks as a function of age. So this is in red, dust mass in disks, so the components, the solid components in disk, as a function of the stellar mass from very low mass stars to solar mass stars here. And in blue, you have essentially the same relationship for exoplanetary system, evolved exoplanetary system, assuming that the planets have a core similar to our own Jupiter, essentially, because most of these planets are giant planets. And you see that basically, throughout the mass range of stars, from very low mass stars to solar mass stars, you always have a consistent picture that the mass that you measure in these disks seems to be lower than the mass that you need to form planets. Okay? Then you can even look, you can question the conversion of dust mass from exoplanets, but you have exactly the same thing if you look around brown dwarfs in the solar vicinity. So Proxima b and TRAPPIST-1 have planetary system that is several Earth masses. And if you look at disks around young brown dwarfs, they have much lower mass. Okay, so again, the masses at 1 million year, 2 million year is already too low to explain the amount of mass. And even if you don't believe these integrated measurements, because you can say, okay, maybe it's concentrated all in one point, you're doing extrapolation and so on. For some samples, we have been able to basically resolve the surface density of dust as a function of radius. For example, look at this. This is the sample of solar mass stars, so from 0.7 to 1 solar mass, roughly speaking, in one of these star-forming regions. This is the minimum mass solar nebula, okay? And these are the measurements that we were able to do, okay? The thick line is where we do actually measure, and the dotted line is somehow the extrapolation. And again, with the one exception, all what we measure is at least 1 order of magnitude below the minimum mass solar nebula, okay? 1 or 2 orders of magnitude. So this means that unless we are drastically wrong on a number of things, and we can discuss in the question what might be wrong, this means that planet formation has already happened. Okay, so you have already converted the solids into planets, because otherwise you don't explain the planets. Okay, so planet formation does not occur as I have been discussing in the simple picture at the beginning, does not occur in this class 2 phase. It has to start very early on. It has to start when you are still very young and you have a lot of material. And so observing those very early disks is critical to understand planet formation, but unfortunately it's not trivial. It's not trivial for a variety of reasons that are connected to the statistics, because of course this is a short phase of disk evolution, and so there are few objects, and also is difficult for optical depth reason, for technical reasons. So what we have done as part of EcoGAL, we said, okay, let's basically try to understand this from a theoretical standpoint, the formation of disks and what properties they should have from a theoretical standpoint, and then compare it with the observations. So this is one of the early works done at COA, essentially, in which basically they run numerical simulations of the collapse of a clamp that forms many cores, and each core, as they call it, the nomenclature can vary, but in the end you form stars, and you form stars with a disk around it, a very young disk, because you are really into the 10 to the 4 year here. And so here you have a zoom in this simulation. Each dot there is a young star, and the color scale is a density representation of the cloud, of the gas density. If you zoom, you arrive at around one object, you see the little young star, and around it a nice disk. And so you can ask your question whether this disk, what are the properties of these disks, and how it compares with the general observations of young disks, which is not trivial to do. So basically we spent quite some time in trying to bridge the numerical simulations to the observations through post-processing, as we call it. So basically you first transform your simulation, which is physical units, into the emission through the radiative transfer processes, and then you simulate observations out of these things, and you try to answer your question whether what you measure at this stage is really close to what you know is in the simulation. So this is a series of papers that we have been working on this, because it's not a trivial thing. The basic answer that you have in those two top diagrams is that if you have the right angular resolution, you're actually able to measure the disk sizes, which, I remind you, is an important parameter, because our disk is small. Our disk has to be small. You can measure the disk parameter, the disk radius, sorry, but measuring the mass is very hard. It's very hard because at this stage, the material is so dense, and the disks are so massive that you are basically optically thick, and so you need to correct for this factor. And so we are still working on this. We are hoping to combine different observations at different wavelengths to resolve the degeneracy. Okay, so this is a work in progress for that part, but for the part of the sides is important. Once you have formed this disk, then you can basically use this as starting condition and then let them evolve as a disk with planet formation and normal disk evolution through the transport of angular momentum and mass, accretion to the central star, ejection of material, and so on. Of course, this is not yet possible to do it for millions of years in a simulation. And so the step that we are following after this is to do a population synthesis based on very simple 1D description starting from these complex simulations and predicting what you expect to see in different population of disks to understand the properties, especially the initial conditions looking at the evolved populations. This is still work in progress on some aspects, so I don't have all the answer. One of the answers that I have is this one on the radii, because as I showed you, the radii are a bit more solid to measure than other things. So this one is still as of today, one of the largest and more homogeneous survey of disk radii as a function of various parameters in one star-forming region. And basically, one important parameter that you have is the ratio between the disk in the solids and the disk in the gas. Here is plotted as a function of the disk in the solids. And if you look at our own solar system has to be in this box at the beginning, okay? So a radius of the order of 30, 50 astronomical units, and a ratio of the CO over dust disk, so gas over solids, of the order of 2, okay? So the basic answer is that, wow, yes, there are some disks that are in this box, even in star-forming region. So this is an important result. Then you try to understand with your models what type of disks should be there. And the simple answer that you get is that none of the models fit in that area. Okay, so there is still a lot that we need to understand in terms of disk formation and evolution, which is something that we are trying, as I said, to do as part of ECOLAB. Note that this plot is logarithmic now, while that one is linear. So basically, these which are the models here are the dots, okay, and the little squares are the same observations, plus 1 or 2. And so basically, most of the models are above this line, and this is not coincidental. This line is essentially separates the models in which you include dust evolution and the ones where you don't include dust evolution, which you expect to have dust evolution. So indeed, you expect all to be above this line, where there are a few, but critically not our own planet, not our own planetary system. Okay, so this is something that we are still trying to grapple with at the moment. Okay, this is just a representation of where are the two stages of planetesimals formation in our own solar system compared with the ages of the populations. I just want to forget for a moment this axis. I just wanted to compare the age of the populations. Here are a few star-forming regions. This plot is from a survey, but it's from a review by Manara et al. In PP7. And basically, we have young star-forming region in a range from a fraction of a million year, 1 million year, to 3 million year, and 5 to 8 million years, okay? And the formation of the different bodies in our own solar system are in these two boxes. This first box, roughly speaking, is the formation of the first planetesimals, the ones that then get differentiated, okay? So, unfortunately, we cannot observe this phase in our normal star-forming region. We need to really look at the very, very young disks to study this region, and that's where our combination of numerical simulations and observations will be important. What we can probe in these star-forming regions, where we can have a better measurement, at least of the dust content and the disk-planet interaction, is the formation of undifferentiated planetesimals and the formation of chondrules, the time of formation of chondrules. Okay? So this is what we tried to analyze. I don't want to show this. I want to show this. These are two key diagnostic plots for different star-forming regions. Again, each point is a population of disks at different ages, from 1 million years to a few million years, as I showed before. And basically what we are showing these plots are basically the medians of the populations of disks and their dispersion, okay? So just a global population. What you would expect in this plot, which shows the mass accretion rate onto the central star as a function of time, essentially. So basically the viscous evolution of the disk, which transports material within the disks and accrete onto the star, which regulates the long-term evolution of the disk in principle, is the exponential decay that you expect to happen, okay? There is one caveat that we will discuss later on if we have time, but it goes down correctly. This is the gas, essentially, is proportional to the gas surface density. In the simple accretion disk theory, the mass accretion rate is related to the total gas mass in the disk. So you have this decline of the gas mass. This is, on the other hand, is the dust mass, inert masses as a function of age. As you see, there are more points. This is related to the fact that we don't have accretion measurements for all the star-forming regions, but the basic red, blue, yellow, and green are the same samples as the other plot. And well, the thing that you see is that in these plots, you don't have this simple relationship of decline as you have in that, but you rather have, if you look at, for example, at this plot where we have better statistics, which is essentially fraction of a solar mass star, which is the most abundant. You have essentially an apparently odd situation in which you have an increase of the dust content and then a decline. Okay? So there are various ways to interpret this, but one of the things that we tried to ask the question, okay, let's suppose this was work done by mostly by Diego Turrini, who was here many years ago, well, a few years ago, and a student from Padova, Lia Bernabò. We asked this question, okay, let's assume that we actually have a very fast planet formation. So we have this formation like in our own solar system, where you have a lot of the dust that goes in planetesimals early on, okay? And so this dust has disappeared, so the mass has gone down in dust, which is what I observe. And then I start forming planets. The planets will interact with these disks of planetesimals. What is going to happen? What is going to happen is that the orbits of the planetesimals will be excited, and so collisions will be enhanced. That's the bottom line. Okay? So this is one example of one of the models that was run by Diego and Lia, where you have the blue dots are planetesimals and the two colored dots are planets. They start to form early on, 0.5 million year. At 1 million year, they have already big planets, and basically the disk-planet interaction basically excites the orbits of the planetesimals. Here you have eccentricity and semi-major axis, so you have a lot of planetesimals in eccentric orbits at this critical time, and these collide with the other planetesimals and creates new dust, and the collisions are also possibly the source of the chondrules, okay, because you dissipate the energy in the collisions. And these are two plots that show essentially the secondary dust production that you have through collision in this system, in this simulated system. As a function of age, you have essentially a peak at between 1 and 2 million years when you grow the bulk of the planetary mass, and as a function of radius, close to the position of the planets, obviously. Okay. So if you have this model in mind and you try to put this onto the graph, this is what you have. This is the planetesimal formation that we assume is very fast. So in the absence of everything else, you would start with an amount of dust, let's say, which is consistent with the minimum mass solar nebula for the solar mass stars. And then it would drop very fast before 1 million year to negligible amount. because it grows into planetesimals. But then here you have the formation of planetary cores. You have this secondary dust, which basically regenerates the dust in the system, and then it maintains the dust at the current level. So that's an idea that could explain the observations of disks and could basically tell us that the chaotic processes and the dynamical history of our own solar system is not unique, but is typical of any disk where planets are forming. Okay, so if there are planets, where are they? Okay, so this is the first image of a protoplanetary disk. Remember, we did this, we decided, okay, we are doing science verification of the longest baselines with ALMA, so the highest angular resolution. We should not scoop the science of anyone, so we take the most boring disk, the one that should have no structure, is bright, constant peaked. Let's do the image of this. And then they came back with this, and we at the beginning were worried that they had done something funky with the calibration of the data and the imaging. But in the end, this was the famous first image of HL Tauri, which is basically a disk still significantly young, so 10 to the 5 years old on the young side of disks, which shows in the dust all these ring structure, which might be created by the disk planet, might or might not. I mean, there are many explanations again, but it might be created by this planet interaction. So of course, the day we saw this, we picked up our phone and called the friends in Arcetri to say, okay, just point the LBT to HL Tauri. We will find the massive planet that shapes this disk. They tried, and we didn't see nothing. Okay, so I said, okay, maybe they are too little. So we modeled it with rocky planets and say, yes, you can do it with rocky planets. But then this image keep coming, no? So that's the second disk. Not only you have the rings in the dust, but you also have some disturbances in the gas, which is most difficult to concentrate. You need large planets. And so I said, okay, let's, we cannot call LBT anymore because we already had them wasting one night. Let's call the KEC, the guy at KEC. We try there and we don't see nothing. So the third thing, okay, let's do one with a big hole. You know, a big hole, you need to have something big inside. So this time we went to ISO, nothing there as well. He discovered a background star far away, but no planets inside. So no one will answer to the phone. No, exactly. Nobody's answering the phone anymore when they see my number. So I said, okay, I've done all I could do here. And so, so far, I think the only truly confirmed by many independent observation system that have planets is young disk with planets is PDS-70, where you have these two planets that have been observed at many wavelengths, so they are confirmed. While all the other, there is a couple of other candidates, few other candidates, but not many. So the question is why there are not that many, in spite of all the presence of all this substructure. And this is our answer. We try to model this, and basically the conclusion of our modeling is that unless, let's see what I can show you. Well, this is let's look at the top one, which shows the contrast in the case of TW Hydra, and this one shows the contrast in the case of HD 16396, so two disks, two very famous disks nearby of these of the observations, so the observational limit up there, and in the curves are what we expect for planets of different masses. Okay, so in the top one, TW Hydra, for example, if you have a relatively small planet, 0.5 solar mass, you're always below the contrast level, especially when you are in the inner region of the system where the extinction is actually dominating. The extinction from the disk is actually dominating. So one of the problems that we have is that in the infrared, it's very hard to overcome the extinction from the disk. So of course, then we did like Star Wars, no? When you don't see the planet, you look around it, and if there are gravitational disturbances, there must be something. And so that's what we try to do with ALMA. This is the first attempt to basically see a disturbance in the Keplerian motion of the gas, localized in both radius and azimuth, which is basically a sync pot of a point mass in the disk in that position. Okay, and there are several candidates now of this. We even basically created a systematic approach to measure this over the years, which is the work of a student that have developed basically a statistical framework to identify these localized disturbances and to relate them to the mass of the planet and their position in the disk, because you have to take into account that the gas emission does not come from the midplane. This is technicality. And this has been applied, or is being applied actually, to the ExoAlma large program. This was devised to basically search for these disturbances and planets. The outcome, which will come soon, but is still that the planetary candidates are still not very abundant. So there are still few candidates at 1 Jupiter mass or above. And one of the problems is still that we are tracing the outer disk. So we are really tracing the regions of the disk that are farther away than 50, 80 astronomical units, and planets at these distances from the star are very rare, also in exoplanetary systems. So I think that the key here in this science will be to basically go, before I go here, to go at high angular resolution, both in the millimeter, if we can, which is not trivial, and in the infrared to try and identify the bulk of the planetary population, which from exoplanetary surveys is around few astronomical units. So it really requires very high angular resolution. Okay, still going back to our own solar system, one of the key ideas is that Jupiter formed the snow line. It's very hard to get the constraints on the snow line. This is the first observation of direct measure of the snow line, of the water emission from a protoplanetary disk that we published last year, and we are following up. And basically is indeed in this, again in HL Tauri, but it is consistent, this emission is consistent with the inner disk. It's still not trivial to connect this with the snow line, because the snow line is on the midplane, and this one is coming from the atmosphere of the disk most likely. So there is still work that needs to be done in this area. So if we look back at our original thing, I have not yet talked about clustered environments. The fact that the early solar system need to be small and massive is a bit in difficult situation compared with the exoplanetary disks, for two reasons. The first reason is, well, the good of this is that the sizes are not totally uncommon, but the difficult thing is that finding the mass and measuring correctly mass and size very early on, which is something that we still have to work on. One key question is this about the early growth of solids and the persistence in the disk. So the growth of the CIA and then persistence of the chondrules in the disk. I think now with this idea of this dynamical mixing, we are in a good situation in terms of trying to reproduce the long-term presence of these large grains, because you reproduce them essentially. The difficult aspect is to understand how you can form and keep the CIAs very early on and mix them throughout the disk, which is something that you have to do to basically explain what you observe in the solar system today. And so these are areas in which we are working. I want to just quickly flash, because I'm very late on this. I want to flash three things. The first thing is that we are starting really to probe these young disks, starting from the properties that you expect to have in the simulation. There you have this numerical simulation, which predict very hot disks and very high accretion rates out of these disks. We tried to measure the temperature profile and the accretion properties in a set of disks. These are two very young papers from the last months, sorry. This one is published, and this one is submitted from EcoGal. This one is one of the first direct measurements, so not related to modeling, of the temperature as a function of radius in one of these very young objects, showing that we are going down to basically 20 AU from the protostar, so really into the planet formation region. And the temperature range that we measure between 100 and 300 Kelvin is consistent with the simulations of some of these disks. And this other thing is the accretion rate on some of those objects, which are difficult to measure because of the extinction that you have, and you have to use the near-infrared probes for this. But basically, we are probing these accretion rates that are consistent with the one in the model and are much higher than the one in the class 2 disks, and the correct thing. So this is to show you that we are going in this direction. This is one of the areas that we are trying to do to constrain the properties of these young disks. And the other thing that we spent quite a bit of energy on, especially the life of Luca Cacciapuoti, that was a student at ISO with us within EcoGal, is to try to understand whether large solids are common in protostars and whether circulation is possible, okay? So it's trying to probe in the millimeter the presence of large grains in the envelopes, so in the outer regions of the protostar. And since it's very hard to form grains here, one of the explanations is that you might basically form the grains in the disk and then circulate them in the envelope through the mass loss rate of the protostar. Okay? So this, for example, correlates one parameter which is related to growth. So up here you have small grains, down here you have large grains with the power in the outflow. And there is a sort of very tentative correlation, okay? This is an area in which we will also continue to work. And finally, one last area where we will continue to work is trying to understand these properties in clusters with techniques that obviously need to rely on not on analyzing each star by itself, by using machine learning approach, which we also developed as part of EcoGal. Okay, I will skip the rest, which is related to the new technologies that we are developing as part of EcoGal to do observations. And I want to close basically on this, otherwise you will all die out of this, which is, I think these are the main questions that we still have in this field for the future. So what are the properties of these small disks? As I've shown you, some of the disks are small, so they are consistent with our own solar system. What are their properties? This is still one question that is difficult to answer. It's difficult to answer because of the concentration of material and also because of the angular resolution of the telescopes. What is the role of environment? Is disk evolution and planet formation different in clusters than in the nearby star-forming region, which is most of the results that I've shown? And this is something that we will get to in the next couple of years with EcoGal. And are the building blocks of life common? This I've not touched this, but is a question that we are asking when we study the chemical evolution of these regions. And to progress, one of the two things which I have not shown, and I'm happy to talk with you if you are interested, that we are doing as part of EcoGal, are actually developing new observing mode for millimeter telescopes and for infrared telescopes. So we are developing the capability of doing polarimetric observation with NOEMA in order to study the disk formation, constrain the disk formation mechanism. And one of the ALMA low-frequency receivers, so that we are contributing to that, of course, not doing everything, we are contributing to that, so that we will be able to study at very high angular resolution planet formation. And we are developing and using new modes for high contrast imaging and also for high contrast spectroscopy in the infrared, which will allow us to probe the atmosphere of these young planets. And I'll stop here because I took already too much time. Stop.
and also from people from home, if they can write the question in the chat, I will read that. So, time for question. I do see Alessio has a question.
Yes, thanks, Leonardo, for a very nice talk. I have a question and a comment, actually, related to the same plot. The plot that you showed, I think from your work, actually, when you showed the probability that the disk of the solar system can be found like within 1% compared to what we see with the say, with the nearby regions, no? So the question is, this plot first has been built assuming that the stars of the other regions are solar-like, or you are just merging all the kind of stars?
No.
I'm imagining different kind of disks.
So these are all the disks. That's why I also show this.
Yes.
Okay. So, but you're right. This is the cumulative distribution of all disk masses. So,
okay.
So the majority is a bit tricky because the majority of these stars will be in the 0.5 solar mass range. Indeed.
So I would be curious on the same plot only for solar-like system.
Yeah. There are not many.
Oh, yeah.
So as you know, in lupus, as I showed in lupus, you have 10, I believe, solar mass stars. If you include, so this is what I showed here. No, yes. In lupus you have how many are these? Well, around 10 solar mass stars, and you see already here that there is one that is consistent. Let's say yes. With the minimum solar nebula, but the others are below. So again, 10%. Astronomy statistics.
Yes. Yes, but that was actually the comment, because it's below 1% combining, let's say, all the stars, no? Yeah. But if we think of the fact that there are around, I don't know, 100 million stars of these sites in the galaxy, 1% of that is not that small at the end of the day, no?
No, true. No, it's true. It's just the question of whether the solar system is 5 to 10% of the total outcomes, or is common. If you look at which one now? At this plot, you have a factor of 10 deficiency also at one solar mass. Okay, so in principle, well, you can interpret this two ways. Solar system is rare. Most stars will form less planets than our solar system, or you can interpret this way, in which all the observed planets are above this threshold, which is again a bias though. And so maybe you had that this solar system amount of planets, let's say, is common, but has to be formed before we get to the stage of the disks.
Thanks.
So, is there any other question?
Let's see, the next talk, thank you. I would like to ask you, your observation and models, looking at the result, do you have a preference between the two main processes at the base of planetary formation and gravitational collapse versus streaming instabilities?
That's a very good question. The problem of gravitational collapse is as far as we know so far, but I will get to that, is not common in the inner disks, because in the inner disk, the disk is too hot to collapse, to gravitational collapse, while the outer disk is actually consistent with the possibility of gravitational collapse. Then the other question is that this is what I just said is based on what we know of the mass distribution of these disks. And possibly in the very early stages, you might have had a more unstable disk. Then a more unstable disk promotes instabilities. Instabilities could be gravitational collapse, but could also be streaming instability. So in fact, basically the fact that all the disks that we observe, many of the disks that we observe, now we have dynamical measurements of some of the disk masses, so especially the brightest disks, because we can measure the profile of velocity of the gas and infer the self-gravity of the disk, not only the gravity of the star. So we have some constraints on that. In these cases, the disks are always at least the measurements are always very close. The ones that we can measure are close to gravitational instability. They are not above, but they are close to instability. So one of the ideas is that disks sort of self-regulate. So you basically accumulate matter, then you have these instabilities that either create how they call planetesimals, or maybe even planets in some cases, but you remain essentially below the level of promoting instability in the gas, because it's the gas, obviously, that we are discussing. No? And so I think, again, to answer this question, we need to look at the young disks, their temperature and mass profile. The fact that the temperature that we derive for these very young disks, sorry, this is a bit slow, but the too many things. The fact that the temperatures that we derive are fairly high, so you have that in the simulations, and in the observations. This seems to suggest that gravitational instability in the terms of collapsing into a planet is going to be very high, because the temperatures are fairly high. Whether this is one case and there are cold disks that can collapse, I don't know.
Any other questions?
Yeah, thanks for the seminar. And okay, you say that our solar system does not look like similar typical of other exoplanet systems, but from all the observations, can you define what is a typical exoplanet system, or each
Yes.
other is different from?
No, you can. To some extent, you can. Okay, let me see if I can avoid skipping all, because it's at the beginning. So let me go quickly here. Okay, so as far as we know today, you can use these observations to infer, these are populations, to infer occurrence rates, okay? So occurrence rates are corrected for bias in principle. And in principle, the only thing that you don't know, so you can correct 0 by something that you don't know about Earth, okay? About the rocky planets, we still don't know. But about Jupiter, this we start to know, because Jupiter is in the region where we can make measurements. As you see here, there is this is actually from 2015, this graph, but the situation is qualitatively very similar. The population of Jupiter analogs, as they are called, is fairly well probed, okay, by essential radial velocity measurements. And there you have the peak, actually, of the occurrence rate of Jupiters, okay, so Jupiter mass planets. And the peak of this occurrence rate is between 1 and 5, then you can discuss the exact boundaries, but between 1 and 5 astronomical units, okay? So this is telling us that formation of Jupiter-like planets at the snow line, which is more or less at this distance, in principle is a common situation. And Jupiter is in this peak. So in principle, Jupiter is not an outlier, a total outlier. Then if you want to ask whether there are Jupiters in circular orbits at 5 AU rather than Jupiters on elliptical orbits at 3 AU, then of course our own solar system becomes more rare, because only 10% of the system has a Jupiter that is consistent with our own Jupiter, in terms also of orbit, not only on the presence.
Okay. Just one last question, and then it's for Stavro. He wrote in the chat. Stavro, if you want, you can unmute yourself and ask your question. Otherwise, I will read it.
Grazie Eugenio, grazie Leonardo per il bel talk. Vorrei chiedere se pensate di fare un confronto tra le dinamiche della polvere nelle prime fasi delle formazioni tra vari dischi, però in funzione della massa dei dischi. Qual è il risultato? In senso, i vari dischi hanno diversa massa, hanno diversa dinamica, vediamo i processi più o meno simili, però la dinamica potrebbe cambiare, perché la crescita può cambiare ovviamente anche a causa di fermentazione di altri processi. Quindi se avete fatto, se c'è la possibilità di ecogare questa parte di ricerca. Grazie.
Sì, ok, so allora, inglese o English or Italian?
Let's go for the English.
Okay, I go for the English. Okay, sorry, no, don't worry, Stavro, I repeat. So basically, whether there is a difference in the dynamics of dust for disks of different age and mass, okay, right? That's how I believe, I understand. So the problem is that the dust dynamics, you can probe only indirectly so far. So you cannot probe directly the velocities, of course, of the dust. So you can probe the dynamics in the sense of probing whether there are asymmetry, so substructures in the gas, which are in the dust, sorry, in the disk, which are created by potential dynamics, and whether you have these large or small grains indicators in disks of different sides around stars of different masses. Okay, so to start from the last point, in all class 2 disks, so we are still above 1 million year, okay, 1 million year or older, you have evidence for grown dust to a certain extent in disks of all around stars of all masses, which is a big puzzle. Because it's a big puzzle because the dust evolution, I mean, the retaining of large grains in disks, in principle, should not work around brown dwarfs. Brown dwarfs, the large dust should dissipate very quickly. And so I think that our conclusion to this is that mechanisms to confine large grains and keep them into the disk need to be at play in disks around stars of all masses, which implies that either you have planets that confine dust grains in substructures, or you have some other way of confining in grain. Regarding the direct measurement of substructures, we do see substructures again around the disks of from stars of all masses. There is one very nice paper by actually one of the Milano former student, Piero Curone, on 1.2 solar mass star with a disk, which shows actually a very clear substructure in the dust and confinement of the dust, which is we model as this planet interaction, but that's a secondary thing. Then the question of age. The question of age is very critical, and you are right on this. The problem of testing the dust in disks, very young disks, is the optical depth mainly. So we are unable to actually measure directly the indication of large grains in the very young disks because the observations are not sensitive to this because of optical depth effects. And for this, we will, well, on one side, we rely to model. On another side, we rely to the circulation in the envelope, as I showed before. So the fact that there are large grains in the envelope is an indication that dust processing is present at very early on. And the last thing is the next generation of observatories going at longer wavelengths might be the only way to probe large grains in these disks. So we look forward to SKA essentially to be able to measure this. Sorry, I don't know whether I answered the question.
Yes. Okay. Thank you very much. Thank you.
Thank you very much. Let's thank the speaker again.